welcome back to the deep dive. Have you ever found yourself wishing you had a crystal ball?
Oh, definitely.
Or maybe wondered how much it would be worth, just to get a little hint about what's coming when you're making a big decision.
Yeah, that edge.
Exactly. Well, today, our mission is to explore just that, how we can sort of navigate all the uncertainty that's just inherent in the world and hopefully make some smarter, more informed choices.
Mm-hmm.
So this deep dive, it's based on sources that really get into some quite advanced aspects of bringing risk into how we make decisions.
Yeah, it's not just surface level stuff.
No, not at all.
Yeah.
We'll unpack the basic idea of expected values first.
Mm-hmm.
Then we'll look at the pretty surprising impact of getting more information, whether it's perfect information, which is rare.
Very rare.
Or more realistically, imperfect information.
Yeah.
We'll also look at handling situations where you've got like multiple uncertain things happening at once.
Yeah, multiple variables.
And finally, we're going to dive into a tool that's, it's powerful, but also often misunderstood. Value at risk, or VAR.
Ah, yes, VAR. Definitely powerful, definitely misunderstood sometimes.
Our goal, like always, is to pull out the really important nuggets of knowledge from these sources, help you get properly informed on these, frankly, crucial topics, give you a shortcut to understanding the complexities of risk.
Sounds good.
Okay, so to really see the power here, let's use a relatable scenario. Let's imagine you're selling ice cream.
Classic example.
It is. And the core challenge is always the same, isn't it? You have to decide how much ice cream to order before you know what the weather's going to be like.
The big unknown.
So our source gives us some probabilities. It says there's a 0.2 chance or 20% of it being cold, 0.5 or 50% for warm, and 0.3, 30% for hot.
Okay. Standard probabilities.
And it also gives us the payoffs, the profit for different order sizes, small, medium, large, under each weather condition. So for instance, a small order on a cold day, $250 profit. But that same small order on a hot day only makes $150.
Right, because you run out.
Exactly. Meanwhile, a large order could rake in $750 on a hot day.
Nice.
But you'd only make $100 if it turns out cold because you've got loads left over.
Right, waste. Okay.
So first step, expected values. This is pretty fundamental. It's basically calculating the long-term average outcome. You weight each possible profit by its probability.
Yeah, what you'd expect to make on average if you ran this scenario many, many times.
Precisely. So doing that math, the expected value for a small order comes out to $195. For medium, it's $380. And for a large order, it's $395.
Okay.
So based just on those numbers, ordering large seems like the best bet initially, right?
Yeah.
$395 expected profit.
Right. That's your baseline decision without any more info.
Yeah.
But what's fascinating here is how much that decision could change if you suddenly got better information.
Okay.
Let's start with the sort of theoretical ideal, perfect information.
The crystal ball?
Exactly. It means you know with absolute certainty what the future holds. So for our ice cream seller, they know exactly what the weather will be before they order.
Wow. Okay, so the power of that is huge. If the seller knew it was going to be cold, they'd obviously order small, make $250.
Maximize for that known outcome.
If they knew it was warm, they'd order medium for $500. And if they knew it was hot, they'd go large for $750.
Makes sense. Always the best choice for the known weather.
So the expected value with this perfect information, you average those best outcomes using the original weather probabilities.
Yeah.
It comes out to $525.
Okay, $525. That's quite a jump from the $395.
It is. And here's the kicker. The value of perfect information is just the difference. $525 minus $395. That's $130.
Right.
And that $130, it's not just a number. It really quantifies the cost of the uncertainty itself. It tells you how much that certainty is theoretically worth.
It puts a price tag on knowing the future, essentially, which then raises an important question.
Yeah.
While perfect information is, a really powerful idea in theory, it's pretty artificial, isn't it?
Oh, completely.
I mean, in the real world, that kind of certainty just doesn't exist. The future isn't perfectly predictable. But, and this is the good news, even imperfect information, like, say, a weather forecast, can still significantly improve our accuracy and our decisions.
Absolutely. So let's go back to our ice cream seller. What if they could get a weather forecast, but it's not guaranteed to be right?
A realistic scenario.
Exactly. The source suggests the seller might look at how accurate past forecasts have been. For example, let's say when a hot forecast was issued in the past.
Okay.
Experience shows that on days when the weather actually turned out to be cold, a hot forecast had been given 30% of the time.
Right, so the forecast isn't perfect. It sometimes predicts hot when it's actually cold.
Yeah. And for days that were actually warm, a hot forecast was given 40% of the time. And for days that were genuinely hot, the hot forecast was right 70% of the time.
Okay, so those numbers tell you the reliability or unreliability of the hot forecast for each actual weather outcome.
It's a subtle but really important distinction, yeah.
So how do we actually use that? Well, our source shows how you can build what it calls a likely weather outcomes table using this historical accuracy data. It basically helps you rejig the original probabilities.
Rejig, I like that.
Yeah, you update your beliefs. So for instance, if a hot forecast comes in today, knowing its track record means our probability for it actually being cold shrinks quite a bit.
Right.
And naturally, the probability for it actually being hot goes up. It's a way to formally refine our understanding based on this new, albeit flawed, piece of data.
Makes sense.
And based on that kind of analysis, if a hot forecast is given, our revised probabilities might look something like this. Probability of cold drops to about 0.128. Probability of warm is around 0.425. And probability of hot increases to about 0.447.
Okay, so the odds have shifted based on the forecast. Now what?
Now, you recalculate the expected values for each order size, but using these new revised probabilities.
Right, so crunching those numbers, the small order's expected value drops to $184. Medium is now $372. And the large order jumps up significantly to $476.
So the optimal decision changes.
It does. With a hot forecast, ordering large is now clearly the best choice. Expected value, $476. So the value of this imperfect information is the difference between this new best decision, $476, and our original best decision without the forecast, $395.
Or just $81.
$81.
Yes.
So what does this all mean for you? Well, it shows that even a little bit of better information, even if it's flawed, can lead to much better outcomes. That $81 is the tangible benefit of getting and using that forecast.
It really quantifies the payoff for reducing uncertainty, even partially.
Exactly.
And this whole idea of constantly refining our probabilities, even with imperfect data like a forecast, it leads us straight into a really fundamental concept in statistics, Bayes' rule.
Bayes' rule. I read a great intuitive explanation of this from The Economist.
Oh, yeah?
Yeah, they described it like a precocious newborn seeing their first sunset. The baby wonders, will the sun rise again? They start with equal odds, maybe put one white marble for rise and one black for not rise in a bag.
Okay, 50-50 prior belief.
Right. Then the sun does rise the next day. So the baby adds another white marble to the bag. Now the chance of picking a white marble, their belief in sunrise goes from 1/2 to 2/3.
Updating the belief with new evidence.
Exactly. Next sunrise, add another white marble. Belief goes from 2/3 to 3/4, and so on. Over time, that initial 50-50 guess gets modified by observation until it becomes almost certain the sun will rise.
That's a brilliant analogy. It perfectly captures how we should consciously or unconsciously update our understanding as new data rolls in.
It really clicked for me.
Yeah. Mathematically, Bayes' rule often looks a bit intimidating, Posterior probability equals likelihood times prior probability divided by marginal likelihood.
The formula can look scary.
It can, but really, in plain English, all Bayes' rule does is give us a systematic way to update our initial belief, that's the prior probability, by factoring in new evidence. The strength of that new evidence is the likelihood. And the marginal likelihood bit on the bottom, it just kind of normalizes everything, makes sure the probabilities add up correctly, and what you get out is the posterior probability, your updated, more informed belief.
Right. Let's make it concrete with that medical test example. This one always trips people up.
Oh yeah, the classic.
So there's a test for a disease, and it's 90% accurate. That means if you have the disease, there's a 90% chance the test comes back positive.
Okay, p-test positive disease, 0.90. Pretty accurate sounding test.
It does. But here's the crucial bit. Only 3% of the general population actually has this disease. The base rate is low.
Right, and that's key. So the surprising result when you apply Bayes' rule is if you test positive, the probability you actually have the disease is only about 22%.
22%? That seems crazy low for a 90% accurate test.
It does, doesn't it? And this raises that important question, why? Why only 22% if the test is 90% accurate? Our intuition really misleads us here.
So what's the intuition breakdown?
Let's think about, say, 100 people. Because the disease prevalence is 3%, roughly 3 people out of that 100 will actually have the disease.
Okay.
Since the test is 90% accurate for those with the disease, maybe 2 or 3 of those 3 people will test positive. Let's say roughly 3 to keep it simple.
Right. True positives.
Now consider the other 97 people who don't have the disease. The test isn't perfect. It has a 10% false positive rate. 100%, 90% accuracy for detecting the disease implies a 10% error rate for healthy people, roughly. So 10% of those 97 healthy people will also test positive. That's about 9.7 people. Let's call it 10 false positives.
Wow. Okay. More false positives than true positives.
Exactly. So you end up with roughly 3 true positives and 10 false positives. That's 13 positive tests in total. But only 3 of those 13 are people who actually have the disease. 3 out of 13. That's about 23%, very close to the 22% calculation.
That makes so much more sense when you lay it out like that.
It's a powerful lesson, isn't it? It combats our tendency to ignore the base rate, how common or rare the thing is overall. Our brains latch onto the test accuracy and forget about the 3% prevalence. Bayes forces us to account for both.
And it's not just for, these kinds of examples. Bayes' rule is actually working away under the hood in things we use daily, like spam filters and email, right?
Absolutely. Classifying email as spam based on keywords is a perfect real-world application. It's constantly updating its belief about an email being spam based on the evidence of the words it contains.
Fascinating stuff. Okay, so far we've been dealing with one main uncertainty, like the weather or having a disease. But often life's more complicated, isn't it? What happens when you're juggling multiple unknowns at the same time? How do you manage that?
That's a great question. When you have decision scenarios involving, say, 2 uncertain variables and each has its own set of probabilities, data tables become a really helpful tool.
The tables, okay.
Yeah, they let you visually map out all the possible combinations of outcomes. And crucially, they help you calculate what we call joint probability.
Joint probability.
It's just the probability of 2 specific independent events happening together. So the chance of outcome A from variable 1 and outcome B from variable 2 both occurring.
Got it. Let's use the concert promoter example from the source.
Perfect.
So this promoter faces 2 big uncertainties. First, how many people will actually show up? Could be 300, 400, or 600, and they have probabilities assigned to each.
Okay, uncertainty 1, attendance.
Second uncertainty, how much profit will they make per person from drinks and snacks? Could be $2 or $6, again, each with its own probability.
Uncertainty 2, concession profit per head.
Right, so our source shows how you can build a simple 3x3 data table, maybe attendance numbers, 300, 400, 600 across the top, and the profit per person figures $2, $6 down the side.
And grid.
And each cell in that grid shows the calculated total profit or loss for that specific combination. Like the cell for 300 attendees and only $2 profit per person might show a loss of, say, $2,000 after accounting for fixed costs.
Okay, so one table shows the financial outcome for every possible combination.
Yes. And then you need a second table, the same size, showing the joint probabilities for each of those combinations.
And how are those calculated?
You just multiply the individual probabilities. So if the probability of 300 attendees is 0.4 and the probability of earning $2 per person is 0.3.
Assuming they're independent events.
Exactly. Assuming attendance doesn't directly affect concession spending per person, then the joint probability for that specific outcome, 300 people, A and E, 2-person, is 0.4 times 0.3, which is 0.12.
Okay, so 12% chance of that specific scenario happening. And you fill the whole table like that.
You do. So now you have 2 tables, one with all the potential profits losses and one with the probability of each of those specific outcomes occurring. And using these 2 tables together, you can answer really practical risk questions. For example, what's the overall probability of making any loss? You just add up the joint probabilities of all the cells where the profit table shows a negative number.
Useful.
In the source example, this comes out to 0.40, or a 40% chance of making a loss.
Okay.
Or you could ask, what's the probability of making a really good profit, say, more than $3,500? Again, you just find the cells in the profit table above $3,500 and sum up their corresponding joint probabilities from the other table.
And that might be, what, 0.26 in the example?
Exactly, 0.26 or 26%.
Right.
So it's a really systematic way to get a handle on the risk profile when you have these interacting uncertainties.
Yeah, it moves beyond just a single expected value and gives you a sense of the distribution of possible outcomes.
Okay, let's pivot now. We're going to dive into a concept that really shook up financial risk management, and one that's definitely seen its share of debate, value at risk, or VAR.
VAR, yes. It's sometimes called the new science of risk management, although maybe not so new anymore. It really emerged as a distinct concept back in the late 1980s.
What prompted it?
A big catalyst was the 1987 stock market crash. That event was just so statistically unlikely, according to the standard models used at the time. It really forced a major rethink in quantitative finance. People realized they needed better ways to measure potential downside risk, especially these extreme tail risk events.
Okay, so what is VAR? What does it tell you?
Well, what's interesting and useful about VAR is that it gives a concise answer to a really important question for anyone managing money, investors, banks, companies. The question is basically, what's the maximum amount I can expect to lose on my portfolio over a specific time horizon with a certain level of confidence?
Okay, so it puts a number on potential loss.
Exactly. It might say something like, with 95% confidence, the maximum loss in this portfolio over the next trading day will not exceed $1 million. Or, there's only a 1% chance of losing more than $5 million over the next month. It gives you a single number representing risk defined by amount, time period, and probability.
Right. How do people actually calculate it? The sources mention 3 main ways.
That's right, 3 main approaches. First is the historical method. This is probably the simplest conceptually.
How does it work?
You just look at the actual historical returns of your portfolio over some past period, say the last 250 days. You rank those daily returns from worst to best. If you want the 95% VAR, you just find the point where 5% of the worst historical losses lie. That loss value is your VAR.
Okay, so it basically assumes the near future will look like the recent past.
Pretty much. Its strength is its simplicity and that it doesn't assume returns follow a neat mathematical distribution. Its weakness is, well, history doesn't always repeat itself, especially not extreme events.
Right. What's the second method?
The variance-covariance method. This one does make an assumption usually that portfolio returns are normally distributed, the classic bell curve.
The bell curve assumption, often criticized.
Often, yes, because financial returns aren't perfectly normal, especially the tails. But this method uses historical data to estimate the portfolio's expected return and, crucially, its standard deviation, a measure of volatility. Then, using the properties of the normal distribution, it calculates the loss level corresponding to the desired confidence level, like 95% or 99%.
Is it easier to calculate?
Generally, yes, especially for portfolios where you know the standard deviations and correlations of the assets. That's why it's quite common.
Okay. And the third one? Monte Carlo.
Monte Carlo simulation. This is often seen as the most flexible and powerful, but also the most complex. Instead of relying purely on historical data or assuming normality, you build a mathematical model for how you think asset prices might move in the future.
A model based on what?
It could incorporate various factors, correlations, even non-normal distributions. Then you use computational power to run thousands or even millions of random simulations based on this model to generate a whole distribution of possible future portfolio values.
Wow, okay.
From that simulated distribution, you can then determine the VAR again, finding the point corresponding to your chosen confidence level, like the worst 5% or 1% of simulated outcomes.
So it uses hypothetical future data, not just past data.
Exactly. It lets you explore what-if scenarios much more effectively, but it heavily depends on the quality of the model you build. Garbage in, garbage out.
Right. Now, the sources also mention adjusting VAR for time. How does that work?
Yeah, that's important. VAR is always tied to a specific time horizon, daily, weekly, monthly, whatever. You can often scale it using a simple rule of thumb based on the idea that volatility, or standard deviation, tends to grow with the square root of time.
Square root of time.
Right. So if you have the daily standard deviation daily, you can estimate the weekly standard deviation weekly by multiplying it by the square root of the number of trading days in a week, usually 5. So weekly S daily 5.
Okay.
And similarly, for monthly VAR, you'd use the square root of the number of trading days in the month, say 20. This allows you to extrapolate VAR estimates across different periods, although, again, it relies on certain assumptions.
Let's use that FT100 index example. Say the daily standard deviation is 2.5%.
Okay.
Using the variance-covariance method, assuming normality, we can calculate the maximum expected losses. For a 95% confidence level, which corresponds to about 1.645 standard deviations on a normal curve, the daily VAR would be 1.645, 2.5%, 2.5%, 9.2%, and the monthly VAR would be 4.1%, 2.20, and 18.4%.
Right. So you can say we are 95% confident we won't lose more than 9.2% in a week or 18.4% in a month.
And if you wanted 99% confidence, which is about 2.33 standard deviations,
then the numbers get bigger, naturally. Daily VAR becomes 2.33, 2.5%, weekly at 13%, monthly at 26%. More confidence requires acknowledging a larger potential loss.
it provides that single digestible number.
Yeah.
But you mentioned controversy.
Yes. If we connect this to the bigger picture, while VAR is no doubt a really powerful tool, especially for professional risk managers who understand its guts, it definitely comes with a big cautionary note.
Okay.
Joe Nocera, writing for the New York Times back in 2009, shortly after the financial crisis, published a piece called Risk Mismanagement. He'd interviewed a lot of risk managers.
And what was his take?
He suggested that VAR, despite its usefulness for the experts, might have actually exacerbated the crisis.
How?
By giving a kind of false security to bank executives and regulators who maybe didn't fully grasp its limitations. They saw this single, seemingly precise number and perhaps relied on it too heavily, underestimating the real tail risks that VAR, especially the simpler versions, might miss.
So it simplified risk almost too much for some audiences.
That was Nocera's argument. And it raises that important question. How can a tool specifically designed to measure risk actually end up contributing to it if it's misunderstood or misused?
That's a really sobering point.
It is. The source material emphasizes that VAR is both easy to misunderstand and potentially dangerous when it's misused or over-relied upon, especially without understanding the assumptions baked into the calculation. It's not a magic number.
That seems like a crucial takeaway. Okay, so wrapping this up, what does this all mean for you listening? It feels like across all these deep dives we do, the one constant is that risk is just everywhere, in every decision.
Absolutely. And these techniques we've talked about, valuing information, using data tables for multiple uncertainties, even a complex tool like VAR, they're all fundamentally tools to help us make appropriate adjustments based on the information we have or don't have. They help us navigate that inherent uncertainty.
Yeah.
And you see this idea of risk adjustment pop up elsewhere too, like in finance with sensitivity analysis or adjusting discount rates for riskier projects. It's a core concept. And honestly, in our current economic climate, these discussions around risk management, stress testing banks, using these kinds of sophisticated tools, they're not just academic exercises anymore. They're happening every single day in the real world.
Very true. So maybe a final thought for you to mull over. As you face decisions in your own life, whether it's something small or something pretty significant, how might understanding the actual value of getting even imperfect information or just being aware of the potential downsides, the pitfalls of a metric like VAR, even if you don't calculate it yourself, how might that awareness change how you approach uncertainty, how you make your next move?
Food for thought.
Definitely. Well, thank you for joining us on another deep dive.
Been a pleasure.
We'll be back soon with more fascinating insights.